Hi, welcome to AB Video 4.4e Part 2, Average Value of a Function. Okay, now example 2, let's say that our bug at t equals 1 second starts over here at -2, and he starts walking to the right, and he's walking very slowly. It takes him a whole second to get to this position here at 7. Then he turns around and walks very quickly, and then the next 3 seconds he gets to this position, which is 4. Now here's the deal. In this case, the total distance traveled will not be the net displacement. The total distance he traveled was from -2 to 7. From -2 to 7 in that first second, he traveled 9 units to the right. And then he traveled 3 units back, but distance is always positive. So we actually went 9 units. He walked for 9 units and he walked for another 3 units. So it turns out the total distance he traveled is 12. But his net displacement, how far away he is from where he started at -2 and he stopped at 4. So he is 6 units away from where he started, but he walked for 12 units. So if indeed the velocity changes sign, in other words, the object is traveling not always in the same direction, then your total distance and your net displacement will be different. Okay, so how do we approach this with the integrals? So here it is. The net displacement is just the end position minus the start position, which is where he was at 5 seconds, which is he was at position 4, minus where he was when he started, which was at 1 second, and at 1 second he was at position -2. So his net displacement is 6, which of course, as we just said, his net displacement will be the integral from 1 second to 5 seconds of the velocity dt, and when you integrate the velocity you get the position, and then when you plug in the 1 and the 5 you get s of 5 minus s of 1. The total distance, on the other hand, is the 9 plus the 3. Now, if you think about it, to get the 9, I did 7 minus -2. To get the 3, I did 7 minus 4. Now, 7 is where he was at 2 seconds. -2 is where he was at 1 second. 7 is where he was at 2 seconds, the position at 2 seconds, and 4 is the position at 5 seconds. So, thinking about that as integration, that would be the integral from 1 to 2 of v of t dt, which will give, well, that's going to give s of 2 minus, because when you integrate velocity, you get position, so s of 2 minus s of 1. And then s of 2 minus s of 5, remember how I always plug in the top number and then the bottom number, so I have to go 5 to 2 v of t dt. But then you know that property of definite integrals, if I switch the position of the limits of integration, then I stick a minus in front of it. So then it turns out that it's the integral from 1 to 2 of v of t dt plus the integral from 2 to 5, I'm going to bring that negative in here now, of negative v of t. Well, if you think about it, you're saying that v of t is positive from 1 to 2, but negative from 2 to 5. That's an absolute value function, is what that is. Okay? So here's what we have. And by the way, on your calculator, you can easily enter a definite integral with an absolute value. That's not a big deal at all. It will be able to figure it out. If you had to figure this out by hand, you would have to break up v of t into its piece function because it's an absolute value. And in this case, v of t, it'll be what's inside when the velocity is positive, and velocity positive means he's moving to the right, and of course he's moving to the right from t equals 1 second to t equals 2 seconds. But on the other hand, the velocity will be negative, which means you'll have to get rid of the absolute values, you'll have to put a negative in front of it, and that happens from 2 to 5, which is when he's moving to the left. Okay, so here's the moral of the story. For motion, the net displacement will always equal the integral from time 1 to time 2 of v of t dt, i.e. time 1 to time 2 of s prime of t dt, which will give s of t, because when you integrate the derivative of s of t, you just get s of t from t1 to t2, and that'll be s of t2 minus s of t1. The total distance, on the other hand, you'll need absolute values. So it'll be the integral from time 1 to time 2 of the absolute value of v of t, which is the absolute value of s prime of t. Okay? So net displacement just integrate the derivative of what you're looking for. Displacement is position, so we integrate the derivative of the position, which is velocity. Total distance, I need the absolute value. Now, if we extend this to non-motion, okay, we have a change of quantity. We have motion, it's the change in position, but here it's just a change of a quantity. The net change will be the integral from time 1 to time 2 of the rate of change of that quantity, because remember, we're integrating the velocity, which is the rate of change of the position, okay? And for total accumulation, you'll need the absolute value of the rate of change of that quantity. Okay, so this is fitting into all of this. If you look at page 294, number 58, which is right here. So here's the graph. It says the graph shows the velocity in feet per second of a decelerating car after the driver applies the brake. So obviously he was going very fast. Is this in miles per, oh, feet per second. I was going to say he's going 85 miles an hour. Hopefully not on a major street, but it's 85 feet per second. He applies the brake, and obviously his velocity, which is what your y-axis represent, the car is slowing down. The question is, use the graph to estimate, it's not an exact, estimate how far the car travels before it comes to a stop. When you see the words how far, you're talking distance. This is time, this is velocity. You know that when you multiply time by velocity, you get distance. So what they're actually asking you for is to estimate the area under the curve, is what they're asking you to do here. Whoops. Okay, so each box, if you look at this picture, the y-axis, let me show you that again, the y-axis is going up by 10, 20, 30, 40. So the y-axis are units of 10, but the x-axis is a half, 1, 1.5, 2. Okay, so this is in seconds, so that's a half a second, 1 second, 1.5 seconds, 2 seconds. This is 10 feet per second, 20 feet per second, etc. So what you're going to do is realize that the distance covered, as you remember, is, and of course he's doing this from 0 seconds to 5 seconds, so there's our times, and we have the absolute value of the velocity, right? That's total distance. But in this particular case, the velocity, as you can see, is above the x-axis, i.e. positive the whole time. I don't need those absolute values. So it's equal to the area under the curve. And believe it or not, what they want you to do is actually figure out how many of these little boxes you have. And I'm not kidding. Okay, so you approximate how many squares there are. So 1, 2, 3, 4, 5, 6, 7 full squares, 8, 9, 10, etc. And then you can take like a half of a square with another half of a square. It's approximately 29, it's not square, they're actually rectangles, 29 of these little rectangles. Each rectangle's area is 1/2 of a second times 10 feet per second, which is 5 feet, and there's 29 of those. The distance covered is 145 feet. Okay, so it's not really that hard to do. You're just counting boxes.